So it's my pleasure to welcome Zaki Leghtas, who everyone knows has made really important contributions to this field and has been ahead of the game for a long time. So we're happy to have him here in BBQ and in the sort of the big wig session. Yeah, so take it away. I'll give you a warning when you've got 5 minutes of your talk left, and you can choose to push into the question time if you wish.
Okay, thanks, Josh. Can you hear me?
Yes.
Okay, I guess you can see my slide. Yes, okay, great. So hello, everyone. It's a pleasure to be here. Thanks to the organizers for the invitation. I will share with you today some recent work we did in my group, and I'd like to acknowledge specifically Clark Smith, who's a postdoc in my group and who almost single-handedly carried out this experiment. So I'm still interested in this fascinating topic of how to protect quantum information. And it occurred to me recently that someone joining the field may wonder, why is this even a thing? Why can I just not take a quantum system that I learned about in my first year quantum mechanics course, like hydrogen atom, and use the two lowest electronic orbitals to make a qubit? And here is the reason why I think this wouldn't work. So if you plot energy versus x being the distance of the electrons to the nucleus, and you look at the wave functions of the two electronic orbitals 0 and 1, you will see that there is a very serious problem, which is that the two wave functions have overlapping supports. What this means in practice is that the region of space occupied by the electron, whether it's in a 0 or a 1 state, is either almost the same or way too close. And the way you can see this as a problem is that if you write down Fermi-Golden's rule to calculate the rate of transition from 1 to 0, it will involve an integral like this, a matrix element, where mu is a operator to which noise can couple. So it's typically a dipole like X or a quadrupole or anything else. And you immediately see that if the 0 and 1 states have overlapping supports, generic mu's will lead to significant overlaps and therefore large rates and therefore short lifetimes. So overall, one can take home that an overlapping support leads to short lifetimes. So the solution to this sounds easy. You might say, well, I mean, just delocalize information. You have a degree of freedom X, just make sure the 0 state and the 1 state are very far from each other. And indeed, this would work. It would prevent transitions from 0 to 1, and this would eliminate bit flips. But there's another problem when you deal with protecting quantum information, is that these energy levels could fluctuate over time by some random amount delta E. And the consequence of this is that quantum superpositions like 0 plus 1 transformed into this kind of superposition where a random phase has been imprinted, and this is what we call phase flips. So you see, this is quite a complicated problem because you need at the same time to have the 0 and 1 far from each other, and you want random fluctuations in the energy landscape to affect 0 and 1 in the same way. And one way you could think of this is making sure 0 and 1 occupy the same space, but we just said that we want them to have overlapping, non-overlapping supports. Well, I'd say quite amazingly, there is a solution to this problem, and this is the beautiful GKP states. And they were introduced in the year 2000 by Josephson and KITE and Preskill, and this is what they look like. You see they have non-overlapping supports because the 0 and 1 are never at the same place at the same time, and they're everywhere at the same time, which means that when you have the energy landscape fluctuate over time, they change in energy in this almost the same way, and therefore this doesn't lead to phase flips. So there's a whole zoo of non-local qubits out there trying to delocalize quantum information over something. There's the GKP states as pursued at Yale and other groups like in Switzerland and so on. There's the celebrated surface code where quantum information is delocalized over physical qubits, which are these blue disks here. And this is pursued by our colleagues in the industry. There is the cat qubits that I think you've heard from many colleagues of mine about, and we work a lot on this in Paris, but I will not talk about this today. There are also many other members of the zoo, like the heavy fluxonium, the cos2 0 pi qubits, and we had a beautiful talk yesterday on 0 pi qubits, or this morning, or from wherever you are. And also our colleagues in condensed matter physics literally try and delocalize information over physical space, real space, like position in meters, by localizing their wave functions at the ends of a nanowire like this. And today I will tell you about a path we are embarking on in Paris, which consists in protecting quantum information by engineering delocalized ground states. So here is what we're trying to do. This is the sort of long-term, ambitious, extremely difficult goal, which is to build this circuit. And you may not recognize these symbols, and that's kind of the point, is that they don't really exist yet, and we're trying to build them. And there is this phase drop phi across this circuit, which is just my degree of freedom. And here is what we're after. We're after an energy spectrum that would look like this, with a bunch of excited states. Maybe they form a band, a continuum, it doesn't really matter. What matters is that there is a spectral gap between these excited states and two states 0 and 1. And similarly to in topology, it's not enough to just look at the spectrum. You now have to go and look under the hood and look at the wave functions. And what the wave functions, what we want is that they look like GKP states, right? So again, we want them to be not at the same place, but everywhere at the same time. So as you can see, a prerequisite is that the states, and in particular the ground state, needs to be delocalized through a phase space. So now let's just go through the various artificial superconducting qubits that have been built over the years and see if they meet this criteria of delocalized ground state. Now, I mean, I find it quite amazing that over these last 20 years of inventions of superconducting circuits, one way or the other, they almost all collapse onto this model where you have an inductor, a Josephson junction, and a capacitor, with different ratios of EL, EJ, and EC. You have a charging energy here, which plays the role of a kinetic energy. You have a parabolic confinement here, and you have a Josephson cosinusoidal correlation. And various circuits lie on graphs like this, where here I've chosen to plot EJ over EC on the y-axis and EL over C on the x-axis. So notice the very important break here, which is marks a break between strictly 0 and finite but small numbers here. So you'll recognize the charge qubit, which was invented in Zaki in the early 2000s, the transmon at Yale in the mid-2000s, the fluxonium, and more recently the blocknium. And there are many others which I have not represented. So let's now go through them and see if they meet this criteria of having delocalized ground states. So the transmon looks like this, where you see the potential, which is the cosine. There is no parabola here, and phase, which is the degree of freedom. And you can see the ground state is very much localized in one place. Okay, it's just this Gaussian-looking state with fluctuations of the phase, which is much smaller than pi. Here is a 2 pi period here. The fluxonium also now has this parabolic confinement that you can see, on top of which there is a cosinusoidal correlation. And the fluxonium also actually has a ground state which is localized in one well, except for very specific bias points for phi external, where you hit a degeneracy and it spreads over 2 wells. But it's usually, well, it's actually never in a regime where the ground state is spread across many, many wells. Now let's look at the blocknium, which was invented and appeared very recently in Vlad's group in Ireland, where you can see that there are many cosinusoidal correlations over this parabolic potential. And now the ground and the excited state actually is spread over many, many wells. Well, many, I mean a few. Okay, so the vacuum fluctuations of the phase are bigger than pi. And you may think, wait, why is this so hard? I mean, if you want this state to look like a GKP state, so it sounds like a prerequisite is that it's delocalized. So let's just make this EL, this parabolic confinement, let's just flatten it out and let the ground state spread. This would mean going to the left on this axis without hitting zero. You want very small EL over EC without hitting zero. And actually, it turns out this is really, really hard. So let me explain why. EL over EC actually, EL over EC can be written in this form, which involves the ratio of the resistance quantum, RQ, to Z, the impedance of the circuit. The impedance of the circuit is root L over C, and the resistance quantum is this quantity, which is 6.4 kiloohms. So if you make these circuits out of metallic plates and wires, and you use only, we call them geometrical elements, you will usually end up with impedances of the order of the vacuum impedance, and usually actually smaller, because we fabricate our systems on dielectrics, which have dielectric constants which are of the order 10. And so the vacuum impedance actually quite a large impedance even for these circuits. And the ratio of these quantities is actually related to the fine structure constants. And I find this problem quite beautiful because, you know, I work with artificial, not artificial circuits, artificial atoms, which are real circuits. And sometimes I have the impression we could build anything we want. But then from time to time, I'm reminded that I am trying to build this in a universe where the fine structure constant is smaller than 1. And this has consequences on what is hard to build and what is easy to build. And particularly making this ratio small is hard. Hard, but not impossible. So very recently in Maryland, they were able to accomplish this nanofabrication feat where they were able to suspend a array of hundreds of Josephson junctions literally in vacuum. They're suspended above the silicon substrate, as you can see in these spectacular SEM pictures. And with this technique, they were able to reach EL over EC of 10 to the minus 2, and which brought them into the regime of ground state delocalization, meaning the fluctuations of the phase of the ground state are bigger than pi. It's spread over multiple wells. And today, what I would like to tell you about is that there is another way, which is what we did to enter this regime. So let me introduce the generalized Josephson elements. Here you have the inductor, and you have a double-crossed hashed box with a little red symbol mu. The Hamiltonian of such a element is the following, where you see you have the usual parts of linear parts, but the cosine potential has a mu inside, which means that the higher mu, the faster the corrugation, right? The faster the oscillation of the cosine. If I write this in the charge basis, you see that it involves the tunneling of mu of Cooper pairs or mu packets of Cooper pairs. Okay, if mu was equal to 1, it would just be 1 Cooper pair at a time. This is the usual Josephson junction. If it's 2, it's pairs of Cooper pairs. If it's 3, it would be triplets of Cooper pairs, and so on. So if I now plot two energy landscapes with the ground state, with mu equal 1 and mu equal 2, you'll see here it's a system where the ground state is spread over, let's say, 1.5-ish wells. And here, if you notice, I've changed the x-axis so that this one here is 2 pi periodic, this one's only pi periodic. And what it means is that I've doubled the number of corrugations. So in units of Josephson wells, this wave function is much more delocalized, right? It's occupying many more wells. This is what we embarked on trying to build, and this is how we did it. And it is based on a proposal by Clark Smith and Michel Devoré and co-workers back when Clark was a PhD student with Michel. And we built it in Paris over the last couple of years. And here it is. So we called it the KITE. It's the kinetic interference co-tunneling elements. And it also looks like a kite, and it echoes its parent, the rhombus. And the kite is basically a loop, which is threaded by external flux theta external. It involves 2 Josephson junctions and 2 superinductances in this loop. and then it is shunted by a linear circuit with an inductor and a capacitor. Now, the relevant degrees of freedom to analyze the circuits are phi sigma and phi delta, which are the sum and difference of the phases across these two Josephson junctions. If we now look at the potential landscape of this system as a function of these two degrees of freedom, I'm plotting it now at theta external equals 0 and pi. So let's just focus on the 0 part. Light colors are minimas and dark colors are maximas. And this is a kind of distorted egg box potential. You'll notice basically that there is a curvature in the delta direction, which is due to epsilon L, this inductance. And there is a curvature in the sigma direction, which is due to this EL and a little bit of an influence of epsilon L. Now, if you look carefully at this, you could basically see that there is a ridge of minimas along the phi delta equals 0. And these minimas are spaced out by 2 pi, right, as marked by these blue dots. And you can see these two paths here, basically the tunneling paths that the particle would take to go from this well to this well. Okay, it's going through this one and they're spaced out by 2 pi. Now, if I bias this circuit at theta external equal pi, I basically get 2 ridges of minimas. And what's quite spectacular is that in the phi sigma coordinates, they're only spaced out by pi. Okay, so a fictitious particle would go in a zigzag if it's operated in the right regime, and it would be slushing between various minimas, which is separated in phi sigma just by pi. And this is where the notion of pi periodic and therefore cos 2 phi comes from. So we made this device, and this is what it looks like. This is the sample box, as you can see. And if we zoom into one of these samples, it looks like this. You have the KITE. We made the symmetric version of the KITE, right, where you have these 2 small Josephson junctions and these inductors that we split in 2. These are superinductances that we made out of arrays of Josephson junctions. Then we spread out our superinductance of the shunting circuit in blue here, and we also coupled. So this is basically the circuits, and this is a readout circuit. So you have a readout resonator with 2 pads which form a capacitor, and a coupling through mutual inductance because they share a certain number of 7 basically Josephson junctions with circuits under study. And here you have some SEM pictures of our typical Josephson junction arrays for the large junctions and our cross-shaped Josephson junctions for the small junctions of the KITE. All this is placed in a sample box, and here there are just some quantities on the circuits, and you can see here in dark gray the on-chip control lines of thread flux in these 2 loops. Now let's probe the system. The first experiment we're going to do is to send a pulse on this antenna and let it reflect off and analyze its phase as a function of the flux threading these 2 loops. And what we're actually going to do physically in the lab is send current in these 2 on-chip flux biases so that IY is essentially mainly threading flux through this loop, and IX is mainly threading flux through this loop. So let's look at some data. This is what it looks like. X is IX, the Y-axis is IY, and in color you have the phase response. And the first thing you can notice is this. First of all, it's kind of a funny looking shape. It repeats itself in 2 directions. You can see many symmetries. There are inversion symmetry points, there are translation symmetries, discrete translation symmetry, and so on. And we can map these symmetries to the symmetries of the Hamiltonian to try and understand where we're sitting in this landscape. And this is what we identify is this axis being phi external, this one being theta external, as plotted here, this cut being a specific theta external equal pi, and this cut being a specific theta external equal 0. And we'll analyze this more in the next few slides. And we can also look at this probe, this antenna mode, as a function of phi external these two different theta externals and see some anti-crossings where you see the resonator frequency is about 5.6 and it's being crossed periodically by energy levels of the kite. And this is how we get our signal. Okay, so now let me explain how we measure the fact that when we go from 0 to pi, we've spread our ground state wave function across more wells. So first of all, I'm going to introduce a notion which is the 0-point fluctuations of the phase, which is this quantity. And as you can see, it's related to the EL over EC ratio, which we said was difficult to make small on, in other words, difficult to make phi ZPF big. Okay, so the way we're going to measure this is the same way that Vlad did this in Maryland, is that we're going to measure a flux dispersion. So let me try and explain why flux dispersion measures phase fluctuations. Here I'm plotting a cosinusoidal corrugation over this parabolic potential. You see the ground and excited states that I plotted in blue and green. And now I'm going to slide phi external, meaning I'm going to slide the cosine corrugation over the potential. As you can see, this cosine corrugation is sliding over this potential. Okay, so let me just play this again. And now try and keep track of these two energy levels, right? And as you can see, they're going to get very close and then they get far again. Okay, and this is due to the fact that the particles is essentially located in one well or the other, so it's being brought down or pulled up by this sliding. Okay, I'll just do it one more time just because it's kind of entertaining. I'll do it back and forth. Okay, so now let's look at this. Yeah, 5 minutes. Okay. Thanks,
two questions.
Thanks. Yeah, sure. Thanks, Josh. Okay, now let's look at the situation where I've doubled, and it might sound like not much, doubling the 0-point phase fluctuations, but as you'll see, it has a spectacular influence. Now, as you can see, there are many, many more wells across which I'm delocalized. If I vary again this phi external, if you look carefully, it looks like the energy levels are almost not moving. Actually, if you look super carefully, they are moving, but just by a much, much smaller amount. In fact, just doubling the 0-point fluctuations from 2 to 4 is actually dividing by 10 the flux dispersion of this transition energy. Okay, so this is what we did in the lab. We embarked on measuring the transition energies between the various energy eigenstates that we could find. The data is in open circles and fits to a 3-mode model, which I'd be happy to tell you about, are in solid lines. And we did this for theta external equals 0 on the left and for theta external equal pi on the right. And maybe I would say the most spectacular feature that one can see is that this flux dispersion, meaning this span of variation of the 0 to 1 transition energy, is indeed reduced drastically from about 1.5 gigahertz to above, just a little bit above 100 megahertz. And this is why we say it's a signature that we've spread across phase space. Now we can go further in the analysis and fit a 1-mode model to this to the low energy eigenstate transition energies, and we can reproduce this kind of features and extract a phi ZPF of 4.2 for the theta external equal pi case, suggesting that our ground state is indeed delocalized across multiple wells. And this number 4 should really be compared to pi. Above pi, so 3.14, above pi means I'm delocalized across many wells. Below pi means I'm localized. And here in a theta external equals 0 case, where you have a large flux dispersion, suggesting that the wave function is actually quite localized in one well. I'll just flash some system parameters if you're interested in numbers. The EJ over EC is approximately 1 and is in the 6 gigahertz range. The EL is much smaller, it's 230 megahertz, but again, it's a superinductance and not a hyper superinductance, right? It's not a super fancy. So the point is that we were able to reach the regime of ground state delocalization without reducing to very, very small numbers this quantity. Here is some transition frequencies, some dispersive shifts, and some lifetimes. I mean, this circuit was not at all designed to optimize lifetimes, so we had some big loops and slippery arrays, so we were not surprised that our clearance times were quite small. Now, just as a perspective, to put it simply, we think that the KITE is a good candidate to serve as this tunneling element for pairs of Cooper pairs or even more, which allows the spread of the wave function. And now we're searching for this other element. So it was very interesting to see in this conference the gyrator and other proposals to couple to the circuits in order to make a autonomously protected qubits. Thank you.
Great. Maybe everyone can thank Zaki with a reaction. The clapping is a little bit underwhelming at a virtual conference, but believe me, we all appreciate it. So we already have one question. So first question is, how does the flux dispersion along the theta external direction, I guess, look like?
Oh, so I see. So if we took cuts along here, it's not, let's say, it's not something recognizable in the sense that along the phi external, it looks like fluxoniums in different regimes. Theta external, one way you could try and guess what it would look like, sweeping theta external would sweep this ridge with respect to the other. So there is the two symmetry points, which we kind of intuitively understand are the 0 and pi, where they alternate, or where the minimum alternates over pi or 2 pi. But if it's just some random quantity, I wouldn't say I have an intuitive explanation for what it would look like, and it's not something we measured. I would maybe like to emphasize for that measuring these kind of spectra, for those who are familiar with fluxonium measurements, I'm sure they would recognize this, is that it's very difficult to measure these kind of spectra, because for every phi external, the whole system is a new system. For example, the readout resonator itself shifts, so we need to track it, calibrate our readout measurement, and then move on. So we did not sweep along theta external. Yeah.
I see. We've got another question. A few. What would one do to the circuit, I guess, to engineer triplets of Cooper pairs instead of pairs of Cooper pairs? This is from
yes, yeah. This is actually a very exciting thing. So you could do it. You need multiple branches. So the way you could think about this KITE elements is that it's an interference effect. So pi, let's say a Cooper pair tunnels from the left or the right, and if you put pi, it gets a pi, like a bit like the Aharonov-Kasher effect. It would get a pi phase and it would cancel. And if you put 3 paths and I guess bias it, I would say it's 2 pi over 3 probably. So this would be 2 pi over 2, and then I guess probably 2 pi over 3. Then you would get a destructive interference, and then you have triplets. Then the biasing would start getting complicated, but it would be a very interesting experiment to do.
Okay. So there's another question. Could you explain what the inductors in the KITE provide, as opposed to the rhombus of junctions, where in that case also theta equals pi leads to tunneling of Cooper pairs?
Oh yes. So okay, mathematically, I'd say what the epsilon L provides is this, let's say, parabolic confinements in the delta direction. Unfortunately, I don't know who asked the question, but they're absolutely right that we could have used a rhombus. The reason why we preferred the KITE is that with a rhombus, this would be replaced by Josephson junctions, and therefore you would have metallic islands in between here. You see, if I had a junction here and a junction here, this metallic island would be isolated, or just, linked to the rest of the world through small junctions, and it would suffer from charge noise. So this is the sort of the fluxonium trick of tying down the two ends of a circuit. Like, we basically tie down isolated electrodes to ground through large inductors. So it's for charge noise reasons.
Great. Last question. So can you give hints on the role of symmetry in KITE? how close must the pairs of JJ's inductors be in values?
Yes, so thanks. Yeah, this is also a very interesting question. So in our case, we got it to 3%, I believe. Let me just check. Yes, 3% between the two EJs. What this does in the data, as you can see here, is that this is supposed to be, if they were perfect, it would be very obvious that this is pi periodic. This does not come down completely down to here because of this asymmetry. If this was really a problem, the asymmetry for whatever application you want, you could make an array of them. There are some beautiful papers by Lev Yoffe and Benoit Dussault over the years, and Rutgers group, where they showed that stringing in series multiple rhombi kills exponentially the cosine phi term. If it's a problem for you, this is what I would do.
Great. Well, thanks again for agreeing to speak. It was an excellent talk. And yeah, hopefully we see you in person soon.